Okay, guys, so it's 2 minutes past 6:30, so we might just kick off. So once again, you're all very welcome, and thank you all for joining. Just for those of you who don't know me, my name is Daniel O'Keefe, and I am the chairman of the Structures and Construction Division of Engineers Ireland. And we're delighted to host a presentation from Ecocem, and I'll now introduce you to our two speakers. So our first speaker is Susan McGarry, who is a Director of Public Affairs and Sustainability at Ecocem Group. She's a chartered civil engineer who was formerly Managing Director of Ecocem Ireland. She's involved in committees in the Institute of Engineers of Ireland and represents the Institute within the construction sector group in the Department of Public Expenditure. In 2022, Susan was appointed to the steering group of Construct Innovate and is an Irish Green Building Council ambassador. And our second speaker is John Reddy, and John is a Director of Concrete Technology at Ecocem Group. He is a chartered engineer. He holds degrees in computer science and civil engineering, in addition to an MSc in advanced concrete technology. He has published several research papers and is currently Vice President of the Institute of Concrete Technology. Okay, Susan, I'll hand it over to you, so if you're ready to go.
Super, thanks, Daniel. Those introductions felt like a bit of a competition, like we both have a long spiel beside our names. So great, thanks everybody for joining. So I'm going to give a little bit of background into GGBS, SEMs in general, and then the policy context in relation to the Irish market. So we had recent procurement rules brought in from the Department of Enterprise around green public procurement for concrete. So we're trying to get it wrapped up in about 45 minutes. So we have time for a Q&A at the end. And if you want to put questions in for me or for John, just pop them in the Q&A box below. So just as introduction, Ecocem's been around for a long time. We've been around for about 24 years, very proven business model at this point. We produce about 2.4 million tonnes of GGBS and GGBS-based cementitious products across 4 plants. We have a couple of import terminals as well, so we have full European coverage, and we're associated with a lot of kind of the large-scale infrastructure projects and big names in the industry. So the company is backed by ArcelorMittal, which is one of the largest steel producers, Saint-Gobain, who are one of the world's biggest building materials producers. And then recently we've had investment from Bill Gates-backed Breakthrough Energy Ventures. And the products that we produce have been used in the HS2, the Grand Paris, the Athletes Village for the Paris Olympics. And in recent years, we've signed collaboration agreements with many cement companies and other building material producers, including Cemex, Holcim, and then just last week, Titan Cement. So our focus has moved away from just GGBS solely. We've invested a lot of time and energy into research and development to other SEMs. So we've one large research lab in Paris, and then we've 2 university labs as well in France. So we have 15% of our workforce now dedicated to R&D, and we've invested about 50 million into the program over the past decade. The main goal of this is to accelerate the decarbonisation of the cement and concrete industry through the use of SEMs, the use of them in a more efficient way. And we've also had success in bringing SEMs into kind of uncharted territories that I think John's going to get into a little bit further down in terms of shotcrete mortars, tile adhesives. So areas where we typically dominate by traditional cement, we've had great success with the use of GGBS or other SEMs. Ecocem Ireland, then, we have our plant in Ringsend. It has a capacity of 350,000 tonnes. We have a lab on site and we source our GGBS from Europe, so from Spain and France typically. In the plant there, we produce GGBS, superfine GGBS, which is just really finely ground GGBS, and then blended CEM3 type products. We do a lot of kind of on-site services to facilitate our clients and customers. So temperature match curing, we do a lot of carbon savings, EPD assistance, mixed design optimization, and then the use of our lab is kind of there for our clients and customers as well. And we have the backup of the lab in Paris. We have a couple of innovative products. So we have a new dry mix mortar called DM1X, which I think needs a slightly more catchy name. ACT, which is our latest product that we'll talk about further on. Ecocem Ultra is alkali activated cement, and then we've also been working on a recycled glass and GGBS combination, which we recently had a Engineers Ireland CPD seminar on as well. So in terms of the policy background around GGBS and SEMs, the Department of Enterprise worked with RPS, EY and RKD to produce a really detailed report on reducing embodied carbon in cement and concrete through public procurement. So about 50% of all concrete in Europe is purchased through public procurement. So it would make sense to kind of target this as a key area for reduction in carbon. The key points that came out of the guidelines was that SEM 1 would be slowly phased out unless technically required. And that concrete products, including poured and precast, should specify a minimum of 30% clinker replacement, unless, again, a technical justification is made. And then moving towards whole life carbon assessments for projects over a certain size. So really driving the market on, public sector being a leader in this area, and then hoping to influence the private sector to take on some of these changes too. So the clinker substitution piece being the main kind of point that we took that's of relevance to the use of GGBS. So just to look at that a little bit. So targeting clinker. When it comes to cement production, 1/3 of the emissions are from the energy used to run the kiln. So that's where you can have fuel replacements, alternative fuels, and you can help reduce that part of the carbon footprint. But 2/3 of the emissions from the production of cement are process emissions. So that's part of the chemical process that happens within the kiln. So the only way to really target that 2/3 is to just produce less clinker. Clinker is only about 10% of the mass of your concrete, but it is responsible for about 95% of the carbon footprint. So that's why clinker becomes the number one, public enemy number one that you need to target and reduce. And the best, easiest, most accessible way of doing that is with SEMs like GGBS. Like GGBS, but then there's also others. So I think this is a really important point that the Irish guidelines did not say you need to do 30% clinker substitution with GGBS. It's just that on this island, GGBS is the most available SEM available. So I say SEM, that's a secondary cementitious material. So there's over about 20 is a general number. There's a lot of SEMs available on the market right now. Some of them are available and in use and in the standard, ready to use within current infrastructure. And then some of them are kind of more early stage technology. They might need a little bit more research into how to valorize them, grind them to the best optimization or whatever it is. So you've got things like GGBS, with fly ash, with limestone filler, calcine clays. There's any multiple of them. So there's a little graph there that kind of plots them in terms of maturity and then processing intensity. That came from the Alliance for Low Carbon Cement. So just as a point of reference, you can get a little bit more information from that website there. So it's an alliance of other low carbon cement producers and SEM producers. So the way the SEMs that I'm showing there, they can all be used as clinker substitution within current concrete infrastructure. So the way GGBS is used as a 1-for-1 replacement, these will have their own kind of mixed design optimization that you need to use whatever proportion of SEM with whatever proportion of Portland cement clinker. The idea behind using SEMs is to reduce the overall carbon footprint of cement in advance of the need for CCUS. So CCUS is obviously part of the long-term plan to decarbonize the industry. However, using SEMs right now would mean the amount of carbon you need to reduce at the point where carbon capture and storage is a usable technology is a lot less, therefore reducing the overall cost of CCUS in the end. One way to kind of facilitate the use of SEMs on the market is by moving our standards towards more performance-based standards. So currently right now, within the cement and concrete standards, we deal with quite prescriptive type standards. Construction product regulation, if anyone's involved in standards, will be very aware that that's kind of under review right now. And there's a lot of talk about performance-based standards. So performance-based standards are the best way to kind of utilize SEMs in an efficient way and get them to market. So you've already seen this is the market's kind of moving towards this in the UK with the BSI Flex 350 standard that's recently been announced. And then in the US, you also have the ASTM C1157, which is a performance-based standard for low carbon cement. So we're seeing the standards start to move that way to help kind of get these SEMs to market. So focusing specifically on GGBS as an SEM. So this is your typical concrete mix. So you've got your aggregates, your binder, your water. So that binder is then going to be split up between two. So you split up between your GGBS and your OPC. So GGBS is Ground Granulated Blast-furnace Slag. It's used in combination with traditional cement. to create a binder within the concrete. This is how it's produced. So it's a byproduct from the steel industry. So at the steelworks, there is a blast furnace, which is essentially a large oven, and into that goes iron ore and coke, heated to 1500 degrees. Your iron settles on the bottom, and then the slag settles on top, and that's kind of impurities. So how they know the iron is ready to be drawn off is by checking the slag on top. So before it's even become a product, it's quite quality controlled. That's extracted from the blast furnace, and it's quenched with water jets to granulate it just for ease of movement and storage, and it's stored outside in the yard. In Ireland, that's brought in via ship, so it's loaded onto the vessel and it's brought to our plant in Dublin Port. And all we need to do then is dry it to get that moisture out. So we dry it with natural gas and grind it in a ball mill using electricity. And that's it. It's ground up and it's ready to go to our concrete customers to produce whatever mix of concrete they want. So in the Irish concrete standard, so the ISEN 206, it is known as a type 2 addition, latent hydraulics. That means its setting time is slightly slower than type 1. It's used as a 1-for-1 replacement with Portland cement. And our standard is quite progressive here in Ireland, the national annex of the Irish standard. It allows up to 70% in combination with a SEM 1 or a SEM 2. So that's specifically in the national annex, which might vary in different member states, and in the UK, different combinations are allowed for use. In terms of EPD, so the Ecocem GGBS is the really small rectangle there on the right. So it's about 42 kilos of CO2 per tonne, 42 kilos of carbon per tonne of product. When you blend that and make a SEM 3A, which would be like a 50-50 mix of GGBS and cement, it ends up around 440 kilos of CO2 per tonne. And that's in comparison with the SEM 1, which would be your higher clinker one, which is around 750, 780 kilos. And then a SEM 2, which is just like a higher proportion of limestone in it, so a lower percentage of clinker. SEM 2 is just under 700 kilos. So quite a big difference when you replace a proportion of the clinker with GGBS. In terms of an example of this, a landmark building that I think everyone would recognise is the Convention Centre. So there's about 2,300 cubes concrete poured in this. They had a goal of being the world's first carbon neutral convention centre, with the term of carbon neutral being undefined at the time. So they use 70% GGBS in the substructure and 50% in the superstructure. Specified mostly in the groundworks for sulfate resistance. And the lower heat of hydration because it was quite a large pour. About 11,000 tonnes of CO2 was saved by specifying GGBS and replacing part of the SEM 2 that would have been used in that project. So quite significant savings can be made by just replacing one product. A brief mention of the architectural qualities you saw from the example of the two powders. Portland cement's quite dark grey. GGBS is very light white, so it can be used as a cheaper alternative to white cement. It can also kind of produce a more smoother, defect-free finish as well, because it's just a finer blend. Overall, it can suppress efflorescence, which you can get on kind of red brick wall. It's more for your kind of small scale brickwork. It's better in that way. And then because it's the finer particle within the mix, it kind of becomes the more dominant color. So it'll just give you a much lighter, brighter color. There's environmental benefits to this as well in terms of like the albedo effect and lowering the heat island effect, that you'll get a brighter surface finish, which helps reflect kind of solar, reflects the sun's energy as solar radiation rather than absorbing it and making the heating up the urban environment. There was a terrible explanation of that, but I did it off the top of my head. I haven't done that slide in a while. So that's it on architectural. It looks great. It's a really nice finish. And then in terms of product application, this is just to illustrate it can be used everywhere. Everywhere that you'd have traditional cement, you can use GGBS. And that's even more so now, given the rate of innovation and advancement in the technology that we've had. So everywhere that you would have traditional cement, from roof tiles, adhesives, whatever it is, you can specify GGBS. So I'm going to pass you over to John Reddy now to deal with the technical side of GGBS and the specification element.
Thanks for that. And thanks for the introduction, Dan. And just to go on with the introduction, I'm a member of the Structures and Construction Division within Engineers Ireland, and we're always recruiting. So if anybody is out there and is feeling inspired by this talk and our affability, please get in touch with Dan and join us, because we need members and we need people with ideas and enthusiasm. So please get in touch. And echoing that comment and what Susan was talking about, standardization, this is an incredible moment in standardization for concrete in Ireland. We have the new edition of EN 206 going to start sometime next year, and there will be a call for experts to get involved with that. So if you want to make a significant contribution to the future of concrete in Ireland, now is an amazing time to get involved with the NSAI and the standards committees that are there. So following that ad break, I'll bring you through some of the technicalities of GGBS. Now, this is chemistry, but there's only one chemistry slide, so don't be too afraid. GGBS has the same chemical constituents as Portland cement, and that's why it works so well within concrete, and it works so well with Portland cement in combination. So you can see there from the diagram, it has a little bit less calcium oxide, a little bit more silicon dioxide, and more alumina dioxide. And that means that the performance is similar, but is subtly different. And I'll talk you through some of the differences that are there. And there are chemical requirements according to the GGBS standard, that is EN 15167. So this is a highly regulated product with quality control in place. So the first thing to say about the differences chemically is that in the hydration, that is the reaction when water is in contact with the GGBS and the cement, the solid black line is typical of Portland cement hydration. So when the water and the cement react in that hydraulic capacity, there is heat emitted. You can see that there. What happens with the GGBS is the heat peak is moved to the right. So that means there's more time involved to get there. And that is what is called a latent hydraulic effect with GGBS. So it is hydraulic, but it is latent hydraulic. And that will affect setting time, maybe finishing operations, early age strength development, possibly striking. That's a multifaceted type of thing depending on the temperature, ambient temperature. So for instance, this evening, today, tomorrow, we're down very cold. Concrete in general is going to be slower with or without GGBS. In very warm climates, they use a lot of GGBS to try to slow the rate of set down. So there is advantages and disadvantages towards it, but all of these things can be managed by talking to your concrete producers, looking at program schedules. So these are things to be aware of. We're engineers, we can deal with things and we can put solutions in place to make good results. So this is talking about concrete durability. This is the Pantheon in Rome, which is about 2,000 years old now. So it was built, constructed way before Portland cement even existed, and has stood the test of time. And the busman's holiday, I got to see this about 2 weeks ago for the first time. It was on my bucket list. So this is just to say that the concrete used here used natural pozzolans that Susan was speaking about as an SCM, and volcanic ash from around Vesuvius in that area. So these are cementitious binders, not necessarily cements. And we're really going backwards to go forwards as we look at cementitious SCM, supplementary cementitious materials to reduce the carbon. But they also have a very beneficial effect with the durability and the long-lasting nature of structures that are made with them, like the Pantheon here, which is, as I say, nearly 2,000 years old. So if you look at the different forms of durability, attack, so we have chloride ingress, chloride migration. So GGBS is really excellent in this environment. So we can have chlorides from the sea, chlorides from the icing salts on the roads. And what happens within the concrete is that the GGBS produces more gel. There's more binding gel that closes the porosity of the concrete and stops the ingress of the chlorides to get into the steel, to start that rusting and deleterious effect that will expand and crack and spall eventually. So you can see in the graph, as the GGBS goes up, that diffusion is going down all the time. And that's giving you a longer life to your concrete. And one of the flagship projects, we've many around Ireland and even in Europe now as the company has grown, but the Greystones Marina was a huge project with a lot of GGBS that was inside. The design life extension, and this is taking on for the de-icing salts. So NRA at the time, now the TII, were one of the early adopters of GGBS, and the first project that used GGBS was the Jack Lynch Tunnel down in Cork, followed soon after by the now Mary McAleese Bridge over the Boyne Valley, where they went for a design life of 120 years by using 50% GGBS. So you're looking at value engineering here. You're getting longer life for your structure. You're getting longer time to your first repair, all by using the durability performance of the GGBS. In the acid and sulfate environment, very harsh and aggressive environments for concrete, GGBS performs extremely well. This is because of the chemistry now involved within the GGBS. So there's, as I say, some subtle differences with the chemistry. There's some components of Portland cement that are highly susceptible to this form of attack that aren't within GGBS. So you can see there that even with a 25% replacement level of GGBS, the effect of the expansion from sulfate attack is massively, massively reduced. And this is acknowledged now within the concrete standards and even the cement standard, where a 66% GGBS and above is classified as a sulfate resisting Portland cement. And to the best of my knowledge, the old fashioned sulfate resistant Portland cement is not manufactured in Ireland or the UK, where people now use combinations of GGBS to suit the design codes. Another very important feature of the GGBS is its low heat of hydration. So getting into mass section pores of concrete, things like wind turbine foundations, very deep section pores. At the start of my career, I was very lucky to be involved in two very deep pores, well, three actually, down in the Dublin docks, where we had the convention centre foundation pores that were, I think, over 2 meters deep. 2,500 cubic concrete poured in one single hit for each of those, and then the Point Watchtower, which wasn't built but now is the XO building at the toll bridge. Again, over 2 meters deep, lots and lots of heat being generated, big risk of thermal cracking. And to reduce the heat of hydration from the concrete, the first measure was to introduce 70% GGBS. So you can see the effect here in the bar graph. It also gives you more open time with the concrete. So for these pours that lasted 16, 18, 20 hours, you'd be worried about cold joints as the concrete's going in there. Concrete with the GGBS stays alive for a little bit longer. That reduced the effect of that going forward. And these were excellent pours, very exciting projects to be involved with. These were temperature readings from those. So we instrumented the foundation slabs on some of these pours, and you can see here the effect of adding in more GGBS. It's reducing the peak temperatures, and what we're worried about here is rapid cooling at the extremities causing a thermal shock. So the general rule of thumb is to have a 20 degrees Celsius differential between your concrete at the top or your concrete at the bottom to the concrete in the middle. So by reducing the peak temperature, you're reducing that gradient to the extremities as the concrete cools from the outside. So what you can do also here is you can add extra insulation to the top if you're worried about rapid cooling. Some of the projects we put down some timber ply, maybe some frost blankets, and you're not looking to protect them from frost, you're just to insulate them to stop that rapid heat loss. One of the other forms of durability attack is carbonation. So it is true to say, it would be remiss to say that the carbonation performance of GGBS is slightly different in combination to that of maybe a Portland cement alone. So there is a more rapid rate of carbonation depth, but ultimately at the end of time, it doesn't go so far as to get to the steel. So it carbonates quicker, but it doesn't reach to the steel. Some of the design codes call for a little bit extra cover, maybe 5 mil extra cover, but carbonation now has been called carbon sequestration by the concrete, and we're now accounting for the carbon that's been brought in to some of the structures in some of the models for counting your carbon. In terms of strength development, so the classical textbook Portland cement strength developed concrete, it goes up and it plateaus out at 28 days. The GGBS one in combination, slightly different than the early age strength is more shallow, and it keeps going and developing strength out past 28 days. So out to maybe 90 days, 180 days, you could get 15 to 20% extra strength on your 28-day cube strength. And again, this has very progressively been looked at in the Irish Annex of 206, where we can specify concrete at 56 days rather than at 28 days. And this is a good kind of sleep better at night if you're looking at low cube results maybe coming in at 28 days, that you know with the GGBS in there, you're going to get that little bit extra in there, which can solve a lot of phone calls, a lot of emails, a lot of coring and so forth. So you're going to get this extra bit of strength development with the GGBS. But one of the things that's always said about GGBS is that, you know, it's too slow. We can't use it. Been working on this since it came into use in Ireland. And one of the tools that Ecocem used to work with contractors to ensure they're having a good experience is to use temperature match curing. And one of the nice projects where we've done this, and I myself have done it, and my colleague Aidan Fogarty has done it on many projects at this stage. But one of the nice ones was the lexicon in Dún Laoghaire, the library. This was poured in similar temperatures to what we're experiencing now. With 50% GGBS specified for the marine resistance in the neighborhood and also for the architectural finish. And I don't know if any of you have been in there, but the finish in the concrete is absolutely stunning. And I would encourage you to go there to have a look inside. So the temperature match curing is really a system of giving you the in situ strength of the concrete non-destructively. So you could take out a core, crush it, you'll get the measure, but you're left with the core hole that's within the unit. What we're doing here is we're making concrete cubes similar to what we do for compliance control, checking quality, but we're linking them to the concrete that's being poured. So we have sensors put in place of, it could be a wall, it could be a slab, linked to a control unit and linked to a specific water bath that regulates the temperature of the pour to that of the water. So when you make a concrete cube, normally it's going into 20 degrees centigrade in the lab. You crush it at 7 days, 28 days. You make a cube now, you put it in, and as the temperature rises within the concrete, the water temperature rises, and then you're getting a direct representation. So deep concrete pours, as I showed previously, the temperature is up to 50 degrees. That will not get represented within a standard concrete cube because it's not at the same sort of temperature. So this is really a direct representation of in situ concrete strength. And that gives you information to make decisions around program, striking formwork, back propping, tensioning slabs, post tension slabs, when to put the stresses on it and things like that. So it's really, I'd say, the buzzwords now are AI, but this is something that we've been working with for a large number of years, and this is developed now to maybe concrete maturity. There's intelligent systems that are out there that people are using with just sensors and so forth. But this is what it looks like on site. I always like to go onto site with this because it's something that's very visual, something that people can understand, very simple. They see a cable going into the slab, being run back. You tell them not to turn off the power. You need constant power here. We've had a few instances when people plug things out and different things. So obviously the element doesn't heat the water when stuff like that happens. But a very good system, as I say, very visual, very easy to understand, and you can take the cubes out at any time to test them. So in Dún Laoghaire, they're worried about the striking of formwork. So we were looking at 16 hours, 24 hours, and we went to 40 hours just to show them what they were doing. So the striking requirement in the code is kind of 2 MPa to withstand the mechanical resistance of that formwork coming away. I like 5. That's where the freeze thaw resistance is looking for. It gives you a little bit more strength. So what you're looking at here is a 50% concrete in 5 degrees and lower, which you maybe shouldn't have been pouring the concrete, but we live in the real world and people do silly things all the time. But a delay maybe of up to 8 hours for striking. So sometimes people say we can't use GGBS. It's going to take a week to remove the formwork. Not true. We can look at these things and work better around that. Did another job on a crane base, and here we did a kind of back-to-back standard cured cubes against temperature match cured cubes. So the standard cured cubes are at 20 degrees. The TMC cubes are at this rapid rise of temperature. So as concrete was poured around 10 degrees there, within 2 days, it was up to 2.5 days, 3 days, it was up to 50 degrees centigrade. All that temperature is accelerating the concrete in situ, but is not getting counted within the standard cube strength. So you can see how a decision based just on standard cubes, you'd say, oh, we can't use this, we can't load the crane, we're way behind in program here, we might have a traffic management system in place, and all these things are problems. But when you look at it, apply some engineering principles, you have the strength within there, and you can move actually oftentimes more quick than you have decided to go for. As Susan said, we've a large team of innovators working on our business, a lot of scientists, a lot of PhD people. We've always been innovating. Necessity is the mother of all invention. So we've survived the great crash of 2007, 8, 9, 10, and long-standing. So we have been thinking about how we can find new markets for GGBS, new applications, and so forth. I'll bring you through just a few of them. So this is a job out in Killiney. This is Durkin Homes, 47 passive homes that were built. On this project, they produced a dry mix silo mortar. So the silos that come to site, just the add water and away you go, where they had up to 35% GGBS, and that included an Ecocem activator. So some of our scientific knowledge to allow GGBS to be used so that the same early age strength performance of the mortar would be achieved, so people could lay the right amount of blocks and bricks and so forth. So that was a very nice success and good publicity out of that project. We also produce technologies that are used within tile adhesives. You may have seen there's a company called EcoFusion who now have the world's first cement-free tile adhesive, and that's based on GGBS with some technology inside. Also some grouts, some renders, and a self-flowing screed, and so forth like that. So we're looking at all these applications within housing as we're trying to catch up from a deficit of housing, how we can introduce GGBS, how we can lower the carbon of these materials that are traditionally based on cement alone, and get that lower carbon for the house as we go on. And within housing, we have plenty of concrete blocks. We can put up to 50% GGBS in a concrete block, no problem. Again, a small little activator, liquid activator added to the mix, and that gives the early age strength. So producers can move the concrete blocks, band them, move them, and get them out the site as they would with just a normal cement mix. So these are very low-hanging fruit opportunities to reduce carbon within houses. And then standard precast. Well, standard precast is a very challenging early age strength requirement for concrete. So the whole name of the game here is reuse of molds, turnover, get things out as quickly as possible, maybe twice in a day, sometimes 3 times within a day. So very challenging for GGBS. The benefit of the precast factory is you're in a more controlled environment. You can look to regulate heat. You can add heat. One of the things we developed is a thermal activation where hot water is used in the mixing to elevate the early age temperature. That elevated temperature accelerates the GGBS and allows it to be used at up to 35–50%, depending on the early age strength requirements of the concrete. There's also things like heated beds within hollow cores and floor slabs. So there are chemical admixtures as well. So there's a whole range of things, and these are factories, but they're also living labs. So a very big success story of the Irish concrete industry is our ability to produce concrete, precast concrete with low carbon criteria for the market in the UK. And there's a large number of projects that have benefited from this in the UK. And soil stabilization is another application where we've kind of introduced GGBS, not traditionally used, but there are a number of variety of kind of applications within soil stabilization. So it could be just simply to dry out, stabilize the ground. You might want to add some mechanical strength to the ground. So there's lime and cement combinations with GGBS. There's also solidification, contaminated ports that have been dredged. This is Hoth here. You can see the green grass on the side. That's all reclaimed. So the dredged land has high contaminants from the paint of ships, and landfilling that in the traditional manner is highly expensive. Might have to go to a special designation of waste, probably to Holland. So instead of doing that, they treated it on site with GGBS, which encapsulated the waste, and they were able to use to reclaim the local land and develop that as an amenity. One project that I worked a lot on is development of shotcrete, so sprayed concrete with GGBS. This is probably the highest early age strength criteria within tunneling. Also, shotcrete or sprayed concrete used for stabilization, maybe of embankments, rockfall areas, things like this, covered sheets, covering sheet pile walls and stuff like that. We can now spray up to 70% GGBS that will set within seconds after spraying. So we're injecting an activator at the nozzle in the spraying system. I have a video here of it in action, just a few seconds. So if you can see here, we have the boom, the operator using the robot, and what we're doing here is we're spraying up into a crown test panel, so above head. So this is 70% GGBS being sprayed up and sticking to something overhead. And these are the kind of early age strengths we're getting here. Within 1 hour, 2.5 newtons, depending on the activator, accelerator dosage. 10% there, we're getting 4 MPa within 1 hour, and at 24 hours, we're getting very significant strength in the 20s. What's going on here? Sorry, and this is the piece then after it was in place. So very, very impressive application. And this is again using our science and technology that we've been developing. Susan touched on a product, Ecocem Ultra. So this is an alkali activated material. The novelty of this is that it doesn't sit within any kind of concrete standard. So it's all well and good making something, but how can you get it to the market, which is another kind of an issue, a non-technical issue, but a really important thing. So there are different routes to markets and certifications and so forth. So this is the route we took for Ecocem Ultra. Alkali activated, 95% GGBS with some chemical activators in there. Traditional alkali activation use a form of silicate technology, maybe sodium silicate, potassium silicates. These are very caustic, high pH products, so there's a lot of health and safety concerns around that. We use a sodium carbonate, which is a lower pH, less than cement, less than GGBS, so it's a more neutral base, which has no kind of health and safety. So this project, this is a product that we achieved an ETA for, and then we went and had pilot projects throughout our business on this, some in London, working with some precasters in Ireland, and some in France. But the ultra part is that its carbon footprint is extremely low. So the binder itself is 80 kilos as opposed to, a very high figure there of 850 kilos. But this product is based, as I say, very highly on GGBS, so it's not really scalable, as the GGBS is a finite material in the market. To show you just kind of one of the case studies that we did, these are tunnel segments that were made in France. They had the benefit of steam curing, so they're looking to turn these over 3 times a day. They have very high early age strength requirement. They're at 6 hours. They're looking for 15 to lift. We got 25, and these are the units. So they look really, really good. They made 6 meters of tunnel for this for the Grand Prix. So it's a nice pilot project. Rings were put in place. So this is Ecocem Ultra. So how do we go forward into the future? What is GGBS? There's a big supply question around GGBS. Scale of the problem is to do with Portland cement. So Portland cement is so readily available around the world. When I started my career, I only looked this up recently. Back in 2004, there was 2.3 billion tons of Portland cement manufactured. Last year, 2023, there was 4.1 billion tons. So just over the course of a half a career, we've nearly doubled the output of Portland cement. And as the population grows, as the worlds develop, as the countries and markets develop, that use of cement is forecast to grow. And cement is a great product, all the engineering properties, but we do have an issue, a large problem with the CO2. So to reduce this, the SCMs are hugely important moving forward. So to kind of look at the GGBS supply question, there's a lot of figures out there, but broadly speaking, for the amount of cement that's produced, there's about 10% of that to do with GGBS. So GGBS is not a global solution. It's not being fully utilized at the moment. It's not being valorized in a lot of markets. So you can see here that the forecast going forward is actually for GGBS production overall to increase. But those markets may be in Asia rather than in Europe, where there's more regulation, more green policies coming in place that are affecting the production of steel in different places. The UK, for instance, is shutting down its steel plants, but it's importing all its GGBS from Asia and maybe South America and further afield. The net benefit of that is still that you're getting your low carbon materials. Sea freight is a low carbon intensity form of transport, so the carbon effect from the transport is very negligible compared to the savings by replacing with Portland cement. So GGBS is here, it's established, it's forecast to grow, but it's a big part of the solution, but not all of the solution. And Susan has given you a list of the different SCMs that are out there to do that. In Ireland, we're very fortunate that we've established a very strong supply chain line around GGBS. We've developed the infrastructure to produce it. We have 3 manufacturing sources in Ireland. We have a number of import terminals also. So estimate about 1 million tons of capacity for GGBS within the Irish market. That's not to say that will be the only SCM that's in the market. It's the one that's in the market now, but there are huge opportunities going forward as we look to reduce clinker to introduce further SCMs within the market. We have manufacturing in Dublin. We have a reach to 32 counties. We even export GGBS to the UK at the moment because we're not sold out in our Dublin factory, and we haven't been sold out for a number of years. And we supply concrete, precast, and dry mix mortar industry. But the future towards clinker reduction and decarbonising is to further reduce that clinker. So this is a kind of current state of affairs, a European average. So if you look at the donut graph, we have a clinker component of a normal cement, say an average cement of 75% clinker, 18% of an SCM, and up to 7% limestone filler. That's ground limestone. And that gives you an average carbon footprint of around about maybe over 600 kilos per ton of CO2. So what can we do to further look at this? So what we have done in Ecocem is we've developed a technology called ACT, and it's lower. Its carbon footprint is 7% lower than the existing cements. And what we're looking to do here is utilize readily abundantly available limestone filler and introduce that as a component in the cement. The cement industry have started this process in Ireland, I believe, back to 2005, 2006 with the introduction of CEM2s. We've got a CEM2 AL, which can up to 20% limestone in there. So this is already established and matured. What we're looking at is increasing that amount of limestone and increasing it dramatically. So this is ground limestone as opposed to a burnt limestone, so a very low CO2 impact within the concrete. We're also looking at the SCM component increasing to 30%, and this is interchangeable between markets. So we have 30% GGBS in Ireland. We could have 30% fly ash. Maybe we could utilize some of the things that are in Money Point stockpiled. There is red mud or bauxite residue in Aganish, which could be utilized. We have waste glass in Ireland, which could be utilized. So there's a number of different components or SCMs there, but this 30% could be any combination of those, and that's where our technology comes in, and it's scalable because we can use locally available SCMs or SCMs that are established within the marketplace where the supply chain is strong, and look at that. So we're reducing the need for GGBS by looking at reducing the carbon by the limestone filler, maintaining structural performance and durability by including the SCM, and using the clinker component, the 20%, as an activator to get the SCM working. So this is what Ecocem are working at the moment. We have had a number of years in development. We're now at a TRL level, that's technical readiness level of 8 in your NASA scale of innovation. So we're working on this at pilot scale projects and get this out into the market. And I am currently working on a project myself with a large consortium that's been built. So in London and the UK, London specifically, we have an Innovate UK project called the Decarbonising Concrete Fund. This was a competition launched early this year in January for 3 million total availability, and these are fully funded projects. So there's no money to be put up from the companies. You can get fully funded for this. There was a £500 limit per project, and 7 projects got funded out of 72, which is really encouraging to see so many people were interested in a low carbon concrete competition. And hopefully they'll do another iteration of this to get more of these projects going in the future. But our project is called the Scalable Low Carbon Demonstrator. So what we're taking is our ACT technology and we're building a demonstration project so people can go and so it can be tested, people see it, they can lick it, they can do whatever they want with it, but it's all this chicken and egg scenario. So we're actually going to build something, and hopefully this project and the pilot going forward will be a reference site to go forward. There is, as Susan said earlier, the BS Flex 350, which is a performance-based standard, and that gives us the testing requirements for durability and for strength to prove the performance and validate what's going on there. So our consortium is led by CISC. We have Capital Concrete, who are a local ready mix producer in London. We have Crea Concrete, who are a precast company, obviously in Northern Ireland, working on some precasts. We have the BRE, the British, or the Building Research Establishment in the UK, doing some durability tests. And we have Loughborough University doing the same, and Ramboll with our design engineers. This is the site in Wembley Park. So CISC have been working on this site for, I think, 17, 18 years with Quintain Developments. So the new yellow bits are what's coming on stream, and our little demonstrator will be on that site. And this demonstrator itself looks like this. So it's a small 2-story building. Structure, frame construction. We have the red, pink is in situ concrete. We have the blue, which is the precast, and the yellow is a PT slab. This will be used for hanging facades and demonstrating what the facades look like on site in the future. So we are pouring, very excitingly pouring here next Monday, the 25th, on site with the foundation slab, and the project will run for the next couple of weeks. Final reports coming out in May. So these are some of our contacts for our colleagues within the Irish business. Sally Ann, our new MD, Ed, who works in business development, Andy Christian on the sales commercial side, and Aidan, who works on the technical side of things. And that concludes our presentation. Thank you very much.